Welcome to the first lecture of our course, dedicated to modern Android architecture. In this lecture, we'll talk about the main architectural approaches used across the course. Let's start. First of all, let's quickly define what software architecture is. Software architecture is simply a way how the program code is organized. Here we can think on several different levels: folders organization, files, classes, functions, programming entities organization, and so on. In this course, we'll talk about each of these levels. Layered architecture. Components within the layered architecture pattern are organized into horizontal layers, each layer performing a specific role with the application, for example, presentation logic or business logic. Although the layered architecture pattern does not specify the number and types of layers that must exist in the pattern, most layered architectures consist of 4 standard layers: presentation, business, persistence, and database. In Android, it's usually 3 layers: presentation or view, business or domain, and data layer. Layered architecture is recommended in Android documentation, and it's a natural choice as it's clear and understandable to most developers. MIA is heavily based on a layered architecture approach, and essentially it's a layered architecture with enhancements. Clean architecture. Most Android developers have faced clean architecture in some way. The clean architecture was introduced in 2012 by Uncle Bob on his blog. Since then it was adopted for many systems, and the Android framework is no exception. Key concepts on clean architecture are separation of concerns, dependency rule, onion-style layering. In my experience, I saw several efforts of clean architecture adoption on Android, and in all cases eventually, it was a sort of layered architecture. However, I find the separation of concerns and dependency rule to be extremely useful concepts. That's why we'll talk about them more in next lecture. MIA. Now we are ready to get a definition for MIA. So modern Android architecture is just a handy name for the layered architecture software design pattern, adopted specifically for mid and large-sized Android applications. All my work is based on 2 things. First, Android documentation from Google. Google developers are those who set the trends and foresee how Android evolves. That's why I find this source to be one of the most useful and trusted. Second, 10 years of experience as an Android developer and my recent experience as a senior Android engineer and Android team lead at Unstoppable Domains. The important thing is I don't want to think of this course as a final point of Android architectural evolution. I encourage you to develop applications and get real-world experience. Implement, change, refactor, observe and learn. I hope this course will help you to find your Android architectural style. Next in this section, we'll do a quick recap of Android architecture in Android and a short overview of Android Compose. Welcome to the lecture on the clean architecture overview. Many articles on Medium describe how to apply clean architecture in Android. I find most of these approaches to be obsolete, but at first, let's review the basic ideas behind clean architecture. Referring to the original Uncle Bob's publication, we can define 3 key principles: separation of concerns, onion architecture, which is an addition to the previous principle, and dependency rule. Let's talk about them. The key concept of clean architecture is the separation of concerns. This means that different parts of codebase should be organized and designed around specific concerns or responsibilities, rather than being tightly coupled or interdependent. In a clean architecture, each part of application business logic is isolated from the outer layers that handle input, output, and infrastructure concerns. This separation allows each part of the logic to be more flexible, reusable, and testable, and also makes it easier to change or update the outer layers without affecting other logic. Dependency rule says that dependency direction of a software system should point inwards, towards the center of the architecture. This means that lower-level modules should not depend on higher-level modules, but rather the opposite. On this image, you may see a simple visualization how each outer layer depends on the preceding inner one, but not the other way around. Key takeaways are: first, the clean architecture is an architectural pattern that emphasizes separation of concerns in software design. This is still up to the developer to choose how they would like to divide the responsibilities. And second, dependency rule says that outer layers should depend on inner layers, but not the other way around. Great! Now we understand the key principles of clean architecture in general. So let's discuss, is it still relevant to Android? Clean architecture principles are still highly relevant to any software system. It's important to keep the principles in mind, but don't get bogged down in the details. Remember, principles can be reused, but the specifics are unique to each system. To create a modern and scalable Android architecture, all you need is a solid understanding of the key principles of clean architecture. And don't worry, we'll dive deeper into the details in the upcoming sections of this course. Thank you for joining me in this lecture. Next lecture will be about Android Compose. Let's go to it! Welcome to the last lecture in this section. Let's dive in. Jetpack Compose is Android's recommended modern toolkit for building native UI. It simplifies and accelerates UI development on Android. Key benefits of Jetpack Compose: less code. Do more with less code and avoid entire classes of bugs, so code is simple and easy to maintain. Intuitive. Just describe your UI, and Compose takes care of the rest. As app state changes, your UI automatically updates. Accelerate development. Compatible with all your existing code, so you can adopt when and where you want. Powerful. Create beautiful apps with direct access to the Android platform APIs and built-in support for material design, dark theme, animations, and more. Why it's a revolution? After 2 years of my everyday work with Compose, I can say that the key benefit for me is that it's much harder to introduce a bug while using Compose. Compose is a straightforward tool, and produced code looks more similar to our human way of thinking than the obsolete Android view system. It becomes easy to decompose your code, which leads to easier testing of composable functions. The last thing is crucial for medium or large-sized systems. They have to be decomposed and ideally covered by tests. This is the separation of concerns we've talked about in the previous lecture. As it's written in course prerequisites, I assume you should have at least a basic understanding of Android Compose to grasp everything we will do in further sections. If you are an absolute zero in Compose, please dedicate at least several hours to getting basic knowledge. Let's quickly talk about where to start in case you are a zero. In case you still haven't tried Android Compose, I recommend you start with official documentation and samples provided by Google. They will give you some initial understanding of the UI toolkit. Google has a good course for beginners, check it out. Also, there are a lot of samples that will help you to understand how it can be used. Check the links in the resources blog for this lecture. So Jetpack Compose is a game changer in Android development. We will heavily rely on it and its functions in the third section of this course, where we will design a modern, scalable, Compose-based Android clean architecture. In the next section of this course, we'll talk about the modern toolset that perfectly fits most of contemporary Android applications. See you there! Welcome to the lecture on functional programming versus object-oriented programming in modern Android architecture. Before we dive into details, let's start by defining the two main paradigms of programming that we'll be discussing today. Functional programming. Functional programming is a programming paradigm that treats computation as the evaluation of mathematical functions. It emphasizes immutability, first-class functions, and the use of pure functions to achieve deterministic behavior. On the other hand, object-oriented programming is a programming paradigm that treats data as objects that have attributes and behaviors. It emphasizes encapsulation, inheritance, and polymorphism to organize and reuse code. Now let's compare the two approaches in more detail. One key difference between functional programming and object-oriented programming is the way they represent and manipulate data. In functional programming, data is often represented as immutable values, meaning it cannot be changed once it has been created. This can make functional code easier to read, as there are no side effects or unexpected changes to data. In contrast, object-oriented programming relies on mutable objects to represent and manipulate data. This allows for more flexible and expressive code, but can also introduce complexity and the potential for bugs if not handled carefully. Another difference between the two approaches is the way they organize and structure code. In functional programming, the focus is on logic and functions rather than on data and objects. This can lead to more concise and expressive code, but may not be as intuitive for developers who are more familiar with object-oriented programming. Object-oriented programming, on the other hand, organizes code around objects and their behaviors. This can make code more readable and reusable, but may require more boilerplate and overhead to set up. So, when you should use functional programming or object-oriented programming in Android? With Kotlin, we have a chance to benefit from both approaches. They are not mutually exclusive, but if properly connected, will allow developers to write scalable and maintainable code. In MAA, data and domain layers are closer to the OOP paradigm. View layer, which is the biggest one, heavily relies on functional programming principles, as Jetpack Compose is nothing more but composable functions. In general, we end up with a mixture of paradigms. As you'll see, it's closer to functional programming though, as we don't use complicated OOP constructions. There are no interfaces and almost no inheritance. In further lectures, you'll see how this mix helps us to avoid excessive code writing, which is common for pure OOP language, like Java. We've covered the main differences between functional programming and object-oriented programming. We've discussed the benefits and drawbacks of each approach, and we've looked at how to choose between the two based on the needs and goals of your project. I hope you found this lecture helpful. If you have any questions, feel free to ask. That's it for now. Thank you for joining me and see you in the next lecture. Welcome to the lecture on the suggested stack for the modern Android architecture. In this lecture, I'll introduce you to the suggested stack for modern Android architecture and explain how each tool fits into the overall architecture. We'll also discuss the trade-offs and considerations to keep in mind when choosing which tools and technologies to use. Tools we will discuss in this lecture: Kotlin Plus coroutines, Jetpack Compose, Jetpack View Model, Compose Navigation, Dependency Injection, Result Library. Let's get started. First of all, I think it's worth mentioning that we use Kotlin language with a mix of functional and OOP approaches, as we discussed in the previous lecture. Kotlin coroutines are used as the only tool for asynchronous code. I do not recommend using RxJava or any similar tool until you are convinced you need them. As my experience shows, most of the developers continue using RxJava just because they work on legacy projects or because they are used to this library. Kotlin coroutines provide a similar experience with a much easier and more intuitive way. Jetpack Compose. There are many Compose and accompanies libraries created. I encourage you to dedicate some time and familiarize yourself with them. Next time you'll be struggling with writing a custom component, most probably it's already implemented in one of these libraries. Jetpack View Model. As per Google documentation, the View Model class is a business logic or screen level state holder. It exposes state to the UI and encapsulates related business logic. Its principal advantage is that it caches state and persists it through configuration changes. This means that your UI doesn't have to fetch data again when navigating between activities or following configuration changes, such as when rotating the screen. As you see, this is a key element of our whole architecture. We will heavily use view models. One more thing, try to avoid shared view models, as they add an increased risk of bug introduction. Compose destinations. Despite the fact that there is a Google navigation library for Compose, I suggest using a wrapper, and in my opinion, Compose destinations is a good choice. Using raw Google library forces writing a lot of boilerplate code that only grows with the number of screens. It's not easy to decompose that code, so after all, you'll end up with a sort of spaghetti code. Let's prevent this using a wrapper. As an outcome, the navigation codebase will be much smaller and prettier. One bold benefit is that library supports nav graphs, so you may build any graphs hierarchy you need, leveraging code decomposition. Dependency injection. This pattern already has become a standard in Android development. For dependency injections, I suggest using hilt or coin with annotations. Both are good, the choice is yours. Result. One last, not obvious missing element is a result library. Consider it as an umbrella for success-failure operations in Kotlin. It's similar to built-in Kotlin result class, but adds several convenient features. You may think of it as just a sealed class with success-failure cases that has many convenient methods for data transformation. We will use this class to transmit data between methods, classes, and layers. In this way, we'll be able to manipulate not only the underlying data, but also any exceptions that happen. It's worth mentioning that the result is not the only available option. You may try using the standard Kotlin result class, or pay attention to the arrow library. All the links for these libraries will be in the resources section for the lecture. In conclusion, we've covered the suggested stack for modern Android architecture. We've looked at the various tools and technologies that make up this stack and how they fit into a scalable, maintainable, and testable architecture that follows the principles of layered clean architecture. I hope this lecture has given you a good understanding of the key components of a modern architecture. This is not the only possible shortlist. I encourage you to experiment with different tools and technologies and see what works best for you. Thank you for joining me in this lecture. I hope you found it helpful and look forward to seeing you in the next lecture dedicated to MVI fundamentals. Welcome to the lecture on MVI fundamentals. In this lecture, we'll talk about MVI and how exactly it can be applied to MAA. So let's get started. The general theory about MVI tells us this is a presentational pattern that consists of three key components: model, view, and intent. Let's talk briefly on each of these components. Model represents data and the business logic of the application. It also maintains a state that can be changed through user action. In our architecture, view model plays this role. View, probably the most simple one, accepts data and displays it. In our architecture, it's a composable function that displays view state from view model. Intent. This is the most misunderstood thing about MVI, as naming clashes with Android's intent. In the Android system, intent is a mechanism that allows applications to communicate with each other. Also, it allows one application to call another application implicitly or explicitly. For example, application A can try to open the Gmail application, but in this case, we should handle a case when Gmail is not installed. Or application A can just try to open any email application and the Android system will do the rest of the work. In MVI, intent is just the intention to make a change to the data by user or the app itself. Unidirectional data flow. In Compose, the UI is immutable. There is no way to update it after it has been drawn. What you can control is the state of your UI. Every time the state of the UI changes, Compose recreates the parts of the UI tree that have changed. Composables can access state and expose events. For example, a text field accepts a value and exposes a callback on value change that requests the callback handler to change the value. Because composables accept state and expose events, the unidirectional data flow pattern fits well with Jetpack Compose. A unidirectional data flow is a design pattern where the state flows down and events flow up. By following UDF, you can decouple composables that display state in the UI from the parts of your app that store and change state. Implementations. Orbit MVI is the recommended implementation. It provides view state and side effect support out of the box. It perfectly works with Jetpack Compose and helps to avoid a lot of boilerplate code. In conclusion, we've covered the fundamentals of the MVI presentational pattern and how exactly it can be applied in MAA. Thank you for joining me in this lecture. I hope you found it helpful and look forward to seeing you in the next one. Welcome to the lecture on designing architectural layers. In this lecture, we'll talk about the early architectural design stage and how exactly it may save a lot of time. So let's get started. Critical thinking. I prefer keeping architecture as simple as possible. Before writing anything, ask yourself the next questions. Why do I write or modify this code? What is my goal in changing this code? Or what am I trying to achieve? In some cases, you may realize you're writing the code just because it was written in some book or an article. Please do not blindly follow concepts. Always use your critical thinking. Number of layers. Considering clean architecture theory and the KEYS principle, I suggest not sticking to a specific number of layers the app should have, but letting it evolve. When your project is in the beginning stage, I suggest not spending too much time creating all the boilerplate code, modules, models, mappers, and so on, but end up with just two layers, data and view. The same approach is recommended in Android documentation, by the way. It will allow you to kick off fast and start delivering the first builds to your client as soon as possible. Who knows, maybe the project will be closed in 3 months and you won't even have to extend the codebase to full-scale clean architecture. Or the client will say, our research showed the functionality has to be completely rewritten. Of course, I hope you won't face such situations, but you've got the idea. Later you may decouple data and domain and separate them if it will be needed. In the next lectures we'll discuss when it's time to do it. But there is no reason to complicate things in the beginning, except for the case when you know for sure this project is going to be crazy big. You have a team, you have finance, and everything is arranged. In this case, feel free to keep the domain layer as well. In the next lecture, we'll see how exactly we can decompose our layers. See you there. Welcome to the lecture on layers decomposition. In this lecture, I'll show what the evolution of layers may look like on your project. We'll start from the easiest case described in the previous lecture, data and view layers, and proceed to more complex cases. So let's get started. In most cases, in the early stage, your architecture should be as simple as possible. That's why it's a good idea to have only 2 layers at first. At the bottom, there are data sources, where data flow is starting. Then it consolidates in repositories. View models should directly use repositories, but avoid using data sources from view models. So your dependency will look like this, from up to down. View models depend on repositories, and repositories depend on data sources. Complete data view architecture. When you realize you have too much logic in your repositories of view models, you may consider separating it to use cases. To keep the architecture as simple as possible, leave use cases on the data layer for now. Do not bother yourself by dedicating one more layer. Start with easy things. Now your dependency will look like this. View models depend on use cases depend on repositories, and repositories depend on data sources. Let's call it complete data view architecture. The next logical step is to encapsulate use cases in a separate layer. Technically, it can be separated inside a domain module. The dependency flow starts the same as on the previous chart. Encapsulating use cases in their own module may have its benefits. Now your view layer depends only on the domain layer, so data models and logic will be used only in the data layer and cannot leak to the view. In other words, introducing a new layer and module emphasizes the separation of concerns and makes it harder to misuse app components from the lower layers. On the previous slides, view layer was represented only by view models. This is incomplete, of course. In a real-world application, view model just represents the view state and acts like a model in the MVI pattern that we've discussed. On the top layer of the dependency hierarchy, there are composable functions that display the data. Everything that the user will see on the screen goes under the composables rectangle on the chart. The last thing I'd like to talk about in this lecture is the possibility to introduce a shortcut. By shortcut, I mean a dependency side effect. A typical user case for this is the usage of settings repository. This repository may use shared preferences or data store data sources. Often a composable needs just to read-write this data directly, without any addition logic or computation. In this case, a developer has a choice, whether to call view model from composable and let it access repository, or inject the repository directly to composable. Both of these ways have pros and cons. If the repository is accessed from view model, there is no dependency side effect introduced. But more code should be written for this, and that code should be covered by unit tests that doubles the effort. That's why another way is possible, to introduce a side effect. This is a possible scenario as well, but you should be careful with it. First of all, understand, this is a side effect, but not a pattern you should follow. You should try to write less such code, and each time you introduce a side effect, you should understand that at some future point, when it will be time for refactoring, this has to be fixed. In the next lecture, we'll dive into the data layer and see exactly how it can be implemented. Welcome to the lecture on the data layer. In this lecture, we'll see how exactly the data layer can be implemented. We'll discuss possible options and look at the test project that I've created. So let's get started. The data layer is the lowest layer in our architecture. Also, it's the farthest layer from the user. As the name says, it's a home for your data. And more specifically, the data is born in data sources. Here is an example of the data sources for the average Android application: API, database, data store or shared preferences. Other possible options: Android key store, file assets, and so on. Depending on application complexity, the list of the data sources may become pretty big. And the natural question is, how one data source can live alongside others and not clash with each other. Let's talk about models. I propose to have separate models for all data sources. It will help us to separate the concerns and make data sources more flexible. Also keep general models in the data layer and map data source models to data models. As an example on this slide, we have 4 data sources, and models of each have its prefix. For example, API data source models have the prefix API, and assets data source models have the prefix asset. In a couple of minutes, I'll demonstrate this in a real example in Android Studio. Repositories. The next level of data manipulation happens in repositories. This is where data sources are used. At first, hold most of the business logic in repositories. Later, separate it into use cases. Repositories also should be covered by unit tests. I know what you're thinking about. Show us some code. Okay, let's look at the code. Let's start our test project development with simplified data view architecture. Let's go! So we'll start from the bottom and go to the top. The bottom in our case is data layer, and we'll start from the test model. Test model is just a simple data class which holds some dummy string. And we have two mappers here, from API test model to test model, and from DB test model to test model. As these prefixes may say, these models are from API data source and DB data source. And let's go to API data source. This is API test model. First of all, pay attention. This is internal data class. We don't expose it to outer layer. It holds, in this example, just the same dummy string. But pay attention to the comments. The example may be much more complex, like you may have dozens of serialized name annotated properties here. And also we have a couple of dummy API interfaces here that just mock retrofit interfaces. And API data source, it joins two APIs, so it gets the data list from one API, it gets another list of data from the second API, and also it adds its own additional API test model. It wraps everything into result success. In case of failure somewhere here, the result failure will be sent, and we return this to the caller. Okay, that should be clear. Now let's go to DB data source. Everything is pretty the same. Very similar test model. I would like to pay your attention that even your data source test models look pretty similar. It's always better to have separate models for each data source, because here you will have different annotations, you may have slightly different fields, because you don't need to store everything that comes from API in local database. Most probably, of course. So we have this DB test model. We have a couple of dummy interfaces for the room database, like a couple of DAOs. And we have DB source that joins information from these two DAOs, like DAO1 get data, DAO2 get data, and it adds its own DB test model. Data store data source is the most simple one. I just didn't want to complicate the things, so it just holds a static string. In real life, it may store it in data store or directly in shared preferences. So this is it with data sources. Pretty simple. Just follow the rules, keep everything separated, don't reuse models between different data sources. The next level is repository. Our modern repository has all these data sources inside, so they are injected: API source, DB source, and data store source. In our dummy example, so it just joins everything. So we get a list of data from API, we map it to our test model. We get a list of models from database, we map it to test model. And then we join this list from API and database with another additional test model, which we create from data store. This is it for the data level. So modern repository is the upper layer of data. Let's see where it's called. It's our view model. View model is located obviously on the view layer. The repository is injected into it, and we call repository getData method inside view model scope launch. Default method allows us to provide two callbacks. for success case and for the failure case. In case of success, we get the list of test models, and pay attention that test model is a public model. So it's exposed to the view layer. And API test model and DB test model, they are internal, so they cannot be exposed. The leak isn't technically possible. Okay, so in our view model, in case of success, this list is just logged into a logcat, and that's it. In case of exception message is logged. So I tried to keep this example as simple as possible to concentrate on the architectural things. I didn't want to put a lot of unnecessary stuff here, so just bare bone architectural example. Thank you for joining me in this lecture. In the next one, we'll proceed to the domain layer. See you there! Welcome to the lecture on the domain layer. In this lecture, we'll see how exactly the domain layer can be implemented. We'll discuss possible options and look at the evolution of our test project. So let's get started. In the previous lecture, our repository was used directly from view model. Now let's imagine a situation when the repository contains a lot of logic. So we decide to decouple that logic and move to a dedicated use case class. As for now, for simplicity, let's keep use case class in the data module as well. Let's look at how the code will change. So now we have this dummy use case that is located inside data use case package, and as you see, it just does the same that was done from view model. So it gets the data and just return it to the upper layer, to the caller. Also we have some dummy delay, so we simulate some intensive computational operation here. So this is it for the use case. Our view model has changed a bit. Now we inject into it not a repository but a use case. Here the code is pretty the same. So we just call invoke method on the use case and get either data or exception. Please pay attention that in this sample the repository is already internal. That means that it's impossible to call it from view model, and only use case can be called because it's public. This solution may work for a while, but as the codebase will grow, at some point of time you'll realize that the time for separation has come. The next logical step would be to separate use case into a dedicated domain module. Let's see what it looks like. First of all, now we have a new domain module. Our use case has been moved into it. Also for convenience, we have interfaces that our use cases may extend. Also I changed the dependency flow. View layer app module does not depend on the data module anymore. It depends on the domain one. And domain depends on the data. That means that in this architectural setup, our modern repository has to be public again. But that's okay, because only domain depends on the data. So repository can be used only in the domain and not from the view. Also our test model was moved to the domain layer because view doesn't depend on the data, so it doesn't have access to the test model, and inside the data we have now data test model. Again, each of the data sources may have its own test models, but they are mapped into the data level test model. So these models under this package, they are for the whole data layer. And this one in the domain, this one can be exposed to the view. The view model looks exactly the same like in the previous example, except of one thing. The import has been changed. Now we import use case from the domain, not from the data. So this is the only thing. In the next lecture, we'll talk in details about the view layer. This is probably the most complex layer of our test application. So get ready. Welcome to the lecture on the view layer. In this lecture, we'll see how exactly the view layer can be implemented. We'll discuss possible options and look at the evolution of our test project. I'll demonstrate how to start with the easiest approach and increase the complexity gradually, step by step. So let's get started. The view layer starts from our activity. However, keeping most of the code in the activity only is an anti-pattern and should be strictly avoided. This means we need an approach how to decouple our code. I suggest you thinking in terms of screens. First of all, this is clean and understandable. Moreover, as you'll see, it's easy to store screens and refactor them. So let's talk about the screen structure. Put screen-related files into a separate packages. For example, let's imagine we have a kind of music application. Then view package structure may look like this. Top view package, then screen package, and two packages, song and playlist, 3 screens in each. There are 6 screens available in total, 3 for the song and 3 for the playlist. Now let's talk about a screen. Most of the screens usually have some logic, so they need a view model. As we are using MVI presentational pattern, at first we need to describe our contract somewhere. That means we end up having 3 files. Let's continue our previous example. Contract file contains view state and other contracts related to the MVI approach. We'll talk about it on the next slide. Song details screen contains composable functions that represent the screen. And song details view model is a view model for this screen. Our contract between view and view model consists on 3 parts: view state, side effect, and user action. In our example, view state contains some data that needs to be displayed. Side effect has one-time events that view need to handle somehow. And user action contains the events that flow from view to view model. Here we can see MVI in action. View state and side effects flow from view model to view, and user actions flow from the view to view model. Now let's see how our view can look like. This is an example code for the song details screen. We already saw the contract, and let's proceed to the details screen. The code is quite straightforward. It processes view state and side effect and converts them into composable UI and outer callbacks. This happens in view state and side effect composable functions. As you see, for example, side effect calls on show network error callback if it receives show network error side effect. Now let's proceed to view model. There is no need to dive into details on how exactly it's implemented in this step. Let's concentrate on a general idea right away. We'll dive into base view model a bit later. So our view model is a source of view state and side effects for the view. Also, it processes any business logic through the use cases or repositories. Okay, at this point it should be more or less clear how the screen works. But the next question is, how can we organize the screens? I propose decoupling view layer structure into the navigation and the screens. Going this way, it becomes possible to reuse a distinct screen through the different user flows and even inject a specific user flow related data into it. In this diagram, you may see how composable functions for main activity are encapsulated into a main screen, which is an entry point to the application's UI. Main screen usually contains scaffold with nav host. Then it's possible to have one or more nav graphs, and each graph can depend on any necessary screen. In this way, screens can be reused across different nav graphs, like the screen number 2 on this example. Let's switch to our dummy application and see what its evolution may look like. Here we don't touch any more data and domain. It's finished, done. Now we are working with the view layer. First of all, I've added compose dependency. There is team and there is main screen, which is called from main activity. So main activity just sets main screen as its content. And inside the main screen, we can see scaffold. This is scaffold body with just a simple text in it. Main screen content. As for now, main view model is not connected to main screen anymore. We'll do that later. Now we are increasing complexity. First of all, I've added compose destinations and Orbit MVI to our sample. And let's talk about base view model. Base view model leverages Orbit MVI. It uses it to implement view state and side effects flow from view model to the view. So we have a bunch of helper methods like update state that we can use to update our view state. And we have a couple send effect methods here. Pay attention that everything is logged. So each change of the view state or side effect will be logged. It can drastically change all your production debugging experience. So use the logging. It really helps. Also, I've added name one screen here. This is the first screen, don't mix it with the main screen. Main screen is an entrance for the UI. The next change is navigation. Now we have two nav graphs. The second one is empty, and the first nav graph contains one screen, which is called name1, just for the simplicity. There are some callbacks that we'll use later, and we have nav extensions that will help us to navigate. The name1 screen is pretty simple. It contains just one state. It can either contain progress indicator or button, and other three buttons, they are always visible. The view model is pretty simple. It has our use case that we created before, and there are 4 functions. Each of them just reacts to some user action. Again, for simplicity, I didn't want to make up some names, so I just called them action 1, 2, 3, 4. And we have 4 appropriate functions. For example, this action 1, it shows loading indicator, then it calls the data, and then it sends side effect. If exception is happen, it logs it and sends another side effect. And we can see how this is handled in the screen. So we just have 2 callbacks, and let's see the usage. We came to the navigation. These callbacks lead to the navigation. I hope you are not tired, because now we are going to add even more complexity to our test project. Let's talk a bit more about screen's structure. As you see on the example, we have 2 nav graphs, 1 and 2. And we have a root nav graph. And what are we going to do right now? We are going to add a root screen. It will be inside a root nav graph. And we are going to add 2 more screens. We already have the screen 1. We are going to add 2 more screens, screen 2 and screen 3. Screen 1 will be used from nav graph 1, and screen 3 will be used from nav graph 2. And pay attention that screen 2 is shared, it's reused between 2 nav graphs. This powerful thing gives us an ability to inject some user flow related data into this screen. For example, user go this user flow and they see the screen number 2 with one set of data. Then they go other user flow and they see screen number 2 with other set of data. But it's the same screen, so it's reused. This is awesome. So let's look at the code. As we've told, now we have root nav graph, and it has a root screen. This screen is the most straightforward one. So it has just 2 buttons, open nav graph 1 and open nav graph 2. The first button opens, navigates to the nav graph 1. As you see, it has the screen number 1 and the screen number 2. And nav graph 2, here is it. It has the screen number 2, which is reused, and screen number 3. Let's briefly review our new screens. Screen number 2 has just a text label and a button that can be shown or hidden depending on the user flow we are on. Screen number 3 is the simplest ever, just a text label and nothing more. So how exactly do we reuse the screen number 2? In nav graph 1 we have this destination. It has show next button false, but in nav graph 2 we have again the name to screen with show next button true. And this is the key difference. So in the first nav graph the button will be hidden. In the second nav graph the button will be shown. Let's demonstrate this. Now let's run our application and see how it works. So this is our root screen with 2 buttons. This is it. Open nav graph 1 and open nav graph 2. And now let's open nav graph 1. Here is it. And as you see, our name 1 screen is start destination for nav graph 1. So this is name 1 screen. We have load data button. Let's run it. And we are redirected to screen number 2. Let's check what happens in screen number 1. So when user press this button, the load data user action is sent to view model. View model shows progress bar. It loads the data and it sends go next side effect. And when the screen receives go next side effect, it just calls go next callback, and it navigates us to the screen number 2 with show next button false. So that's why we don't see this button here right now. Now let's go back to our roots screen and open navgraph 2. Now we see the screen number 2, but the button go to next is present, because if you remember, we have it here with show next button true. We can click this button and we are redirected to the screen number 3, because on next clicked callback of the screen number 2 navigates us to this name tree screen destination. This is it. In the next lecture, we'll talk about how to connect layers. I intentionally dedicated time for this topic, as it may save you a lot of time by avoiding unneeded effort. Welcome to the lecture on layers connection. In this lecture, we'll talk about a not so obvious thing that may save you precious time. We'll discuss how we can connect our layers and stop writing boilerplate code. Let's get started. Open any classic implementation of clean architecture on Android, and you'll see that developers often use interfaces to connect layers. As for me, this is a rudiment of Java-style OOP thinking. If you've learned OOP in university or read any book about it, you know this approach encourages a developer to write a lot of generalization code. It can be base classes, interfaces, and so on. That's why a lot of so-called classic Android clean architecture implementations use interfaces. I would like to show you another point of view that will save you a lot of time. I propose not writing interfaces or base classes if you do not really need them. As we told in the lecture Functional Programming versus OOP in Modern Android Architecture, the functional approach may improve your code drastically. Omitting unnecessary components is a part of this. Let's switch to our dummy applications code and pay attention to what we've discussed. Now let's follow the data flow from the lowest layers to the upper layers, from the data to the view. Pay attention to how exactly the layers are connected. For example, let's open our repository and find its usages. As you see, it's called from the use case. We inject the implementation, the exact repository. We don't inject any kind of interface here just because we don't need it. Why should we inject the interface if we don't use it? Of course, if we need polymorphism and we have several implementations but one interface, then yes, we can use base classes and or interfaces. But in case you have the only one modern repository and you don't have anything similar, you don't need the base class or interface. I just would like to show you how it's easy to go to the used class, for example to modern repository. So I just press command and click to it, and I'm inside modern repository. This is why I hate interfaces in most of the cases, because they are just misused and overused. For example, here, if there will be an interface injected, not a repository, I will go to the interface and then I will have to search for interface usages, and only then I will find my modern repository. So the code-based navigation will be overcomplicated in case of excessive usage of interfaces. I mean unnecessary usage of interfaces. The same with our use case. As you see, it extends an interface, but we use it just to simplify the writing of invoke method here. You may study these two interfaces by your own. We won't stop on them right now. So let's find usages for the use case. And again, so it's directly injected into view model. We don't inject any abstract thing here, because it's just not needed. In the next lecture, we'll continue advancing modern Android architecture. We'll start on how to leverage on the data-driven approach for components conjunction. In this lecture, we'll discuss a reactive approach of delivering data to the user. I think its efficiency is highly underestimated in the current Android world. So let's get started. So let's give a definition. What is a reactive data? First of all, ViewModel subscribes to Kotlin Flow and just listens for the new emits. This means ViewModel is reactive as it doesn't proactively request the new data. How to redisplay new data after it's updated? Let's look at a simple example. Screen 1 shows data model A. The user presses something and data model A is updated with a new field. How exactly data update happens and how UI is updated. The algorithm is the next. First, viewModel calls use case calls repository calls data source to update the data. And that's it. As viewModel is a subscriber, new data will be emitted automatically. UI will be updated automatically as well. Pay attention to the difference between dependency and data flows. Dependency flow always go in one way inwards. The data flow is circular though, going in both directions. The picture illustrates what I've told. So the dependency flow goes one way, from the screen to viewModel, use case, repository and data source finally. And data flow, it goes both ways. So some data go from the screen through viewModel, through use case and repository to data source, and here the data is updated. And our viewModel, it listens for the data, and it goes from data source to repository to use case to viewModel, and then it goes from viewModel to the screen. That's why it's circular model, and dependency flow is a one-way model. Now let's look at a more complex example. There are two screens, a list of items and item details. The user opens the item details screen from the items list and changes the data. Then user returns to the items list screen. So how does the data flow happen? The algorithm is the next. Items list viewModel subscribes to data changes. Then details screen viewModel changes the data. Both items list viewModel and details screen viewModel get new emitted data at the same time. No additional actions are required. This is illustrated in this image. In the upper part, this is items list data flow. So items list screen listens to viewModel, viewModel listens to use case listens to repository, and etc. So the next level would be data source. And item details data flow is the same in terms of listening. It goes from the bottom to the top to the item details screen, and when the changes happen, it goes the other way around. So from item details to viewModel to use case to repository and so on. Please note, if an implementation would be done without flow, the items list screen will need to be updated again. To do this, the details screen should send a kind of result to the backstack, and the list screen will update itself when it gets the result. Details screen should also care how to update itself if the data is changed. In our case, no additional actions are required. We don't have to think when to update the data. It's automatically updated in a reactive way. Some tools you'll be using can emit unnecessary data. This is especially actual for the room, as it emits a new result each time a table is updated, not when only rows included in observation are updated. That's why we need an additional filter on flows side. Just add distinct until changed to your room DAO queries. Combine flows. If you have different data sources, you may consider combining them into one of the app's lower level, like repository or use case. Refer to Kotlin Flow documentation for more usage examples. The very easy one from the Kotlin documentation shows us how to combine two flows. So we have flow and flow2. The first one emits numbers, the second one emits strings. Here the method combine combines flow2 and flow1 and explains how exactly we would like to combine these items from different flows. And then we print this. In the next lecture, we'll talk about modularization and why it's one of the most important things in architectural design. See you there! Welcome to the lecture dedicated to modularization. Modularization is the practice of breaking the concept of monolithic, one-module codebase into loosely coupled, self-contained modules. Let's get started with modularization benefits. This offers many benefits, including scalability. In a tightly coupled codebase, a single change can trigger a cascade of alternations. A properly modularized project will embrace the separation of concerns principle. This in turn empowers the contributors with more autonomy while also enforcing architectural patterns, enabling work in parallel. Modularization helps decrease version control conflicts and enables more efficient work in parallel for developers in larger teams. Ownership. A module can have a dedicated owner who is responsible for maintaining the code and tests, fixing bugs and reviewing changes. Encapsulation. Isolated code is easier to read, understand, test and maintain. Reduced build time. Leveraging Gradle's parallel and incremental build can reduce build times. Dynamic delivery. Modularization is a requirement for play feature delivery, which allows certain features of your app to be delivered conditionally or downloaded on demand. Reusability. Proper modularization enables opportunities for code sharing and building multiple apps across different platforms from the same foundation. And let's talk about modularization pitfalls. However, modularization is a pattern that can be misused, and there are some gotchas to be aware of when modularizing an app. Too many modules. Each module has an overhead that comes in the form of increased complexity of the build configuration. This can cause Gradle sync times to increase and incurs an ongoing maintenance cost. In addition, adding more modules increases the complexity of the project's Gradle setup when compared to a single monolithic module. This can be mitigated by making use of conversion plugins to extract reusable and composable build configuration into type-safe Kotlin code. Not enough modules. Conversely, if your modules are few, large, and tightly coupled, you end up with yet another monolith. This means you lose some benefits of modularization. If your module is bloated and has no single, well-defined purpose, you should consider splitting it. Too complex. There is no silver bullet here. In fact, it doesn't always make sense to modularize your project. A dominating factor is the size and relative complexity of the codebase. If your project is not expected to grow beyond a certain threshold, the scalability and build time gains won't apply. Modularization strategy. It's important to note that there is no single modularization strategy that fits all projects. However, there are general guidelines that can be followed to ensure you maximize its benefits and minimize its downsides. A barebone module is simply a directory with a Gradle build script inside. Usually though, a module will consist of one or more source sets and possibly a collection of resources or assets. Modules can be built and tested independently. Due to Gradle's flexibility, there are few constraints as to how you can organize your project. In general, you should strive for low coupling and high cohesion. Low coupling. Modules should be as independent as possible from one another, so that changes to one module have zero or minimal impact on other modules. They shouldn't possess knowledge of the inner workings of other modules. High cohesion. A module should comprise a collection of code that acts as a system. It should have clearly defined responsibilities and stay within boundaries of certain domain knowledge. A good practical reference may be a now in Android application. I already mentioned it in the first section. You may find a GitHub link in the resources blog for this lecture. In this example, there are 4 module types. The app module contains app level and scaffolding classes that bind the rest of the codebase, such as main activity, application, and app level controlled navigation. Feature modules. Feature-specific modules which are scoped to handle a single responsibility in the app. These modules can be reused by any app, including test or other flavored apps when needed, while still keeping it separated and isolated. Core modules. Common library modules containing auxiliary code and specific dependencies that need to be shared between other modules in the app. These modules can depend on other core modules, but they shouldn't depend on feature nor app modules. Miscellaneous modules such as sync, benchmark, and test modules. Please keep in mind, this app is just an example, and in real life you'll always have to balance between having too many modules and having too few of them. Don't do modularization just because it's a fancy thing. Follow common sense and do it only when it's needed. In section 3 dedicated to designing modern Android architecture, we've talked about data, domain and view layers. It's possible to map them to modules directly, and it's a good option while you have up to 3 developers on the team. In case you have more human resources and a huge backlog, you should consider dividing each of the layers into submodules. We haven't talked about common modules in section 3, but usually it's an unavoidable thing. Use it wisely though. If common modules become huge, this is a clear sign of a lack of architectural design on a project. In the next lecture, we'll talk about how to advance the view layer. I'll show you how to decompose it in terms of the structure and packages. See you there! Welcome to the lecture dedicated to advanced view layer. We will dive into the decomposition of view layer components, composables, navigation and features. Let's get started with composable functions. Composable functions are something but pure functional programming. That means on any mid or more sized project, developers will end up having a lot of composable functions. These functions need to be somehow organized. First of all, let's define a couple of terms. The first is the pure composable function. By this I mean a composable function that does not depend on any third-party component, like use case, view model, etc. In this picture, an example of the pure composable is displayed. A huge part of your pure composables will be default composables that are widely reused across the app. They can be considered basic blocks for your upper level composables. The second term is mixed composable function. This is a function that depends on any sort of business logic in your application. In this example, composables depend on the network repository and read-write network state from to it. So this is mixed composable. I'd like to pay your attention that the terms pure and mixed composables make any sense only when we are talking about dependencies. This doesn't have any relationship to stateless, stateful functions, etc. Both pure and mixed composable functions can be either stateless or stateful. Let's don't concentrate on it right now. Dependency is what we are interested in. The first step to decomposition is to separate pure composable functions from mixed ones. It would be great to emphasize this so-called pureness by extracting them into a submodule. This submodule should depend only on Compose, Accompanist and similar libraries. Do not depend on any business logic of your application, as it allows you to write mixed composable functions. In this picture you may see just a reference to how pure composables may be organized in the subpackage. This structure is evolutional and greatly depends on the project. I don't think we should seek a unified structure that fits all the projects. On the second picture you may see the content for the default widgets package. It may be pretty big, especially if your project has a well-developed own design system. Each file can contain several implementations that may slightly vary. If you are questioning what to do with mixed composables, here is a short to-do list. First of all, try to have fewer general-purpose mixed composables. Remember, each mixed composable is a trade-off between the code purity and speed of development. At the same time, don't try to avoid them completely, as it will slow you down. Store these composables where there is access to business logic. The natural place would be the app view package. The decomposition of this package is up to you. Again, there is no silver bullet here, just try to make it convenient to yourself. Navigation decomposition. It may be a tricky thing if you don't use Compose destinations or a similar library. So the first thing is to depend on this library, as we've told in section 3 of this course. After this, you may start thinking in terms of nav graphs. By the way, have you known that you may even build a hierarchy of nav graphs with Compose destinations? Eventually, you'll end up with some sort of nav graph structure like this. This is just an illustration of how nav graphs may evolve. The next level would be to decompose root nav graph. My experience shows this graph may contain a lot of destinations. In case this happens, and these destinations don't belong to any specific nav graph, you may create several files like main screens, general screens, song screens, and so on. Remember, all these destinations are part of root nav graph. They are just decomposed into several files for convenience. In the previous lecture, we've talked about modularization and how it can improve the code. Also, I referred to an example application now in Android. Here is the same picture that demonstrates the modules decomposition of this application. As for me, now in Android is a good reference, especially because of features decomposition. Each feature is placed in its own submodule that isolates it and allows it to focus on a specific part of an application. You don't have to follow the same module's structure though. On your project, features may be a part of the app view package. For example, modules structure for the view layer may look like this. It's really up to you. How do you want to organize them? Any structure is okay, while it follows the principles we are discussing in the course. I hope these references will help you to come up with your own style. In the next lecture, we'll talk about the best practices in modern Android architecture that will help you to become a true master of your code. See you there! Welcome to the last lecture in this section. We'll talk about best practices you may follow or establish to make sure your code is effective and maintainable. Let's get started. I'll never stop talking about KISS and YAGNI principles as they intend to simplify your life. They are vital in ensuring that your systems are simple, easy to understand, and maintainable. Adopting these principles leads to increasing reliability, faster development time, and a focus on the most important features and requirements. This results in lower development costs and higher quality end products. These principles are not only crucial for software development, but can be applied to any type of project or business process. By implementing KISS and YAGNI, you can improve code efficiency and save valuable resources. Don't overcomplicate things. Let these principles guide you to success. Your life, your rules. Introducing rules and standards in software development is extremely important, as it helps ensure consistency and maintainability of the code base. It also encourages teamwork, which makes it simpler for everyone to comprehend and work on the code base. What can be standardized? It's up to you, but I'll give you some food for thought. Here is a small shortlist of possible options. Data flow on the project, packages structure, packages naming, files structure, the same for classes, methods, Git branches naming, etc. Of course, it's impossible to standardize everything, but it's not needed actually. Try to balance. An excessive set of rules can slow down development instead of accelerating it. That's why it's crucial to automate as much as possible. Let's talk about this more. Here Detect comes to the stage. Detect is a static code analyzer for Kotlin. The rules are highly configurable. A point where Detect has to be called also can be adjusted. You may run rules for each app's run as a paracommit hook and so on. Now I'll show you how to configure Detect to be run as a paracommit hook. Also, you'll get my config and can reuse it in your own project. First of all, I would like to say that you should refer to Detect documentation, because this is an evolving project and the way how it can be configured often changes. That's why the best way to figure it out is to go to github.com/detect/detect. In my case, I've made a setup of the latest 1.22.0 version. The setup was pretty simple, so I just added a Detect plugin on the top level of application, and for each of the sub-projects I applied my own Gradle plugin. It takes this config.yml. It already has some predefined rules, a lot of them. Like there is a default config that you can just copy paste from Detect repository, and then you may adjust it. And this one that I'm using, it's already adjusted. So a lot of rules are turned off by default, and I intentionally turned them on because I want them to be checked. Another important thing to consider, except of the config, is reporting. In my case, this is merged report, because before that, each of the modules produced its own report. Now developers of the Detect, they've added a possibility to merge them into a single unified report. It has to be XML file because they haven't found the better way yet. So basically that's it. How to set up a pre-commit hook. Here is a script. It's very simple. The only thing that you need to do is to copy paste this file from the detect folder to .git hooks folder. And that's it. Now I'll quickly demonstrate how detect works. We have our single use case in this test application, and if you remember, there is a delay here. I just replaced delay with magic number, and now I am trying to commit. Just some test commit. This warning is given me by Android Studio, not by Detect. I am just ignoring it, pressing commit anyway. And now the pre-commit hook is called, and it says commit failed with error, show details in console. And here in console I can see that this file get data with logic applied use case on specific line magic number error happened, and it gives me precise description. This expression contains a magic number. Consider defining it into a well-named constant. Okay, now I'll return it, so it will be just delay, and trying to commit again. 4 files committed. So detect passed, no errors occurred, commit succeed. I do recommend using detect on any size project. That's why I encourage you using my detect config. See you in the next section dedicated to testing and debugging modern Android architecture. Welcome to the section about testing and debugging. In this lecture we'll talk about unit and instrumentation tests. I'll explain in detail what should be covered and show you best practices that can greatly simplify your life. Let's get started. At first, I'll remind you that a unit test is a piece of code that verifies the behavior of a small section of other code, the unit under test. However, I prefer the term subject under test, or SUT. Testing happens by executing that code and checking the result. A key difference with other test types is that a unit test is a local test and runs without an emulator, just inside your JVM. They are cheap in terms of computation and effort. That's why we would like to write more unit tests. The percentage of unit tests among all the tests may be from 70 to 100% on your project. The proposed toolset for unit tests is JUnit 4, Mock or Mockito for mocks, Turbine for simplified flow testing, JUnit Assert, Hamcrest or Truth for assertions. I prefer Mock over Mockito as it was written specifically for Kotlin and supports almost all possible use cases you may face. The Turbine is optional, but quite desired to cover lazy data flows. Another thing to consider is the assertion library. You may use the JUnit's built-in assertions or depend on Hamcrest or Truth library. If you don't have a preference, I propose trying Truth, as it's developed by Google with all the consequences. Hamcrest is a good option as well. So let's define what parts of the code are the most critical and desirable to be tested. On the data level, the only thing that we would like to cover is repositories. There is less sense to cover data sources, as they barely contain any logic. But the repository usually has logic inside, and we definitely would like to cover it. The next thing is use case, as it's the primary app component for business logic. Probably it's the best candidate to be unit tested if you have to choose. On the view layer, it's obviously view model, as it contains a part of business logic. Composable functions can be tested as well, if you have the time and capacity to do it. So the final proposed shortlist of what to unit test is on the screen. Repository on data layer, use case on domain layer, at least view model on view layer. You might think about extending this shortlist, however, I do not advise you shortening it. So let's discuss repository coverage. In the screenshot, you may see a simple unit test that checks returned result. Most of the repository tests should check data integrity, as this is the primary responsibility area of the repository. Let's proceed to use case unit testing. Use case tests will look similar to repository, but should concentrate more on the business logic. Unit test functions for use case may be named like fun invoke emits data with correct attribute is home true, and so on. The general naming pattern can be defined like method name, what it does, any conditions that may apply. In these examples, our method name is invoke, then what it does, emits data, does not emit data, sends verification code, wipes all the data. And conditions are with correct attribute is home true, if any part of the output is broken, with ID value, and here we don't have any condition. There is a high probability that use case under test will work with Kotlin Flow. Use a turbine to tackle it. On the screenshot, test awaits for the emitted item, compares it to expected string, and then awaits flow for completeness. View model test strategy is pretty similar to that described above, with the only difference if you are using Orbit MVI. In this case, you'll need several helpers to test it properly. Refer to the Orbit MVI's documentation and our test project for the reference. Let's see how the test functions may be named in this case. So the naming pattern is still the same. The first part is what? User action load data. User action load data. Then what it does, updates view state, triggers side effect go next, triggers side effect show error, and then condition, if operation succeed, if operation succeed, if operation failed. As you see, naming pattern is the same as in previous examples. And view model test may look like this. Here we have test view state extension that helps us to test view state. As you see, we are emulating user action, skipping view state, and then we are awaiting for the next view state, which should be lower than false. Here are some useful tips to help you write more effective and efficient tests. First, give your test functions clear and meaningful names. This way, readers will be able to understand exactly what is being tested without even looking at the code. Follow my pattern. What it does, any conditions. Follow the 3A structure, arrange, act, assert, when writing your tests. I'll leave you a link to a helpful article on this approach in the resources section. I'll quickly demonstrate you what I mean though. So for example, in this test, we have arrange, act, and assert. When referring to the component being tested, use the SUT subject under test naming convention. Try to keep the number of assertions in each test to a minimum, no more than 2-3. If you find yourself needing more, consider breaking the test into smaller, more focused tests. Follow the dry principle when creating data for your tests. If you notice the same data being used in multiple test files, consider encapsulating it in a separate file, such as test model producer. Stick to the KISS and YAGNI principles when writing and maintaining your tests. This way, the process will be more enjoyable and less of a chore. By following these tips, you will be on your way to writing cleaner, more efficient tests that are breeze to maintain. Instrumentation testing. Here I want to be short. Let me break it down for you. Instrumentation tests are not as crucial as unit tests. so if you are short on resources, it's totally okay to skip them. However, if you have the capacity to do both, by all means go for it. Just keep in mind that it may require a dedicated team member to properly and efficiently handle instrumentation tests. Prioritize unit tests, and if you have the extra resources, tackle instrumentation tests as well. The choice is yours. Get ready for a thrilling discussion on resolving production incidents in the next lecture. This is one of the most important and critical responsibilities of every developer, so don't miss out. See you there! Production incident is a rare occasion if you follow all the principles described above and have decent unit test coverage. However, let's talk about how can we prepare to eliminate incidents as soon as possible if they happen. Let's start. I recommend you start by adding Timber as a dependency if you haven't done it yet, and changing all Android util log usages to Timber ones. What should be logged in Timber? Handled exceptions, view state side effect user action change in base view model, screen nav graph change in navigation. Other places you consider to be important. Timber can help a lot with the next step, which is crash reporting. The next important step is to configure a crash reporting tool. It can be something like Firebase Crashlytics, Bugsnag, New Relic, etc. Use something you have experience with, or choose Crashlytics otherwise. While configuring, follow the next steps. Follow the Get Started guide for your tool. Configure it just to be working. Check it sending a test crash and observe it in the web panel. Report what is logged to Timber. To do that, first, configure a release tree for the Timber, and second, log everything that comes to the Timber as a breadcrumb of a crash reporting tool. Breadcrumb is a log that is added to the crash reporting tool on purpose. These logs are stored tied to the user's session. If a crash occurs, the web panel allows to open its details and trace the user's path through the program from the app's launch up to the crash. Logging navigation MVI events allow having the whole picture of what users have done and how they navigated through the app. In case of any production incident, this information can be extremely helpful. Now I'll briefly demonstrate you what we've talked about. First of all, as you see, I have set up Timber. Here, for debug builds, I am set up in debug tree. It just logs everything to logcat through Android util log class. However, for production releases, I have release tree. There is a method log to crash reporting tool. Here I have a to-do set, log to Crashlytics, Bugsnag, New Relic, or your favorite tool. In real life, you will have here one more method like setup. For example, let it be Crashlytics. Here you will do this setup to do, and here you will do something like Crashlytics log priority message and T. It may be not so simple, not in just in one line, but the general idea is like this. All the logging which goes through Timber for release builds will be redirected to your crash reporting tool. Now let's briefly talk about base view model and what is logged here. In my case, I log everything that has any relationship to MVI. This is view state change, this is side effect change, and this is user actions. Any of these changes will be logged through the Timber. The last thing is navigation. As I mentioned, logging navigation changes can drastically improve all your debugging experience. There is this function logging navigation which just does Timber decall. You may go further though. Let's talk briefly about advanced crash reporting configuration. At this point, we've done everything possible on the client side. Now it's time to pump a web dashboard. Depending on your needs, the shortlist of possible actions may include: configure custom views on a dashboard, set up Slack notifications about new crashes or other important events like crash reoccurring, connect GitHub repository to crash reporting tool, open a crashed line just from the dashboard, integrate Jira with crash reporting tool, create tickets in a couple of clicks. I encourage you to spend more time reading the documentation for your crash reporting tool for more ideas and implementation details. One more additional thing that may be nice to have is analytics. It's an indispensable tool when there is a need to analyze user behavior, user flows, make any A/B tests, etc. In terms of tooling, the most obvious choice here is Firebase Analytics. Stick to your company standards though, if there are any. We won't go deep here as analytics configuration differs a lot depending on the project. Just remember this option exists and can be useful for incidents investigation as well. The steps for incident investigation usually look like: first, understand in what part of the application it happens. Narrow the lookup data. The crash reporting tool should help you to understand what file and what line is crashing. Next, read the logs thoughtfully. In some cases, you'll understand what's going on just after reviewing basic logs. In other cases, you'll need to go through the breadcrumbs to understand what the user did. Then try to reproduce. This step is optional, but usually it's nice to be able to reproduce it so the fix can be easily checked. If there is no luck, try additional tools. Use everything: breadcrumbs, information about the user's device or free memory. Try to look into analytics and find something useful there too. Then it's time to fix the bug and test the fix. Think about what parts of the app may potentially can be affected by the fix and notify your QA about it. Release and reiterate. Release and keep watching the bug. Is it gone? If yes, perfect. If not, consider adding more logs in order to be able to narrow the problem in the future. In this section, we told how to make the application as stable as possible and how to prevent and resolve any production incidents if they happen. Congratulations! We've almost reached the end of the course. But before wrapping up, let's do a quick recap of what we've learned and talk about the future of Android architecture. Don't miss it! Whoa! Finally we've got to the last section of this course. Let's do a quick recap of what we've learned. We've learned how to make modern Android applications that follow the best standards for scalability and maintainability. To construct code bases that are simple to comprehend and maintain, we used the layered clean architecture approach to app development. Additionally, we've looked at how the codebase changes over time and discovered important details. We've learned how to create reactive, declarative, and simple-to-test user interfaces using the Jetpack Compose framework and data-driven reactive approach. And finally, we've learned how to test and debug the modern Android architecture. As we are wrapping up, I'd like to summarize the evolutionary approach we've talked about during the whole course. So, start from small. Do not even try to foresee everything from the very beginning, as it's just impossible. You never know what will happen tomorrow. Maybe the business will announce they are prioritizing feature A and sunsetting feature B as it haven't met expectations. Grow organically. Do not turn architecture into your toy. Treat yourself as a doer that helps evolution to express through this project. React to requirements change and readjust architecture on the fly. This is how architecture grows and evolution takes place. Keep architectural tech debt level low. If the time for architectural change has come, plan this change. Do not leave this part of the work unwritten. Create a task, plan, and triage it. In this way, you'll be sure that the change eventually will happen. The ultimate piece of advice is never stop learning. Always work on broadening your horizons. This is a key to your professional success. Now I am working on reformatting this online course to a book. Probably by the time you watch it, the book is ready. All my Udemy alumni can get this book with huge discount. Check it out. Check my LinkedIn for more details. Also, do not hesitate to connect with me. I am glad to expand my professional network. Thank you very much for trusting me. I hope I managed to convey my more than 10 years of experience through this online course. Sincerely yours, Alex Zaitsev. Hey, for those of you who don't want to say goodbye, I recorded this bonus lecture. We'll spend another few minutes together talking about documentation and how can we apply the evolutionary approach to it. Let's start. Let's tackle the easier tasks first and then move on to more challenging ones. Personally, I believe that the simplest way to handle documentation is not to include any comments at all. However, we all know that this approach won't cut it in the long run. That's why having self-documenting code is essential. Self-documenting code means that the class name accurately reflects its purpose. The function name, along with the list of arguments, describes what goes on inside. Local variables within a function have descriptive names that make sense within the context of the function. By following these simple hints, most of the code won't require any additional documentation. However, it's important to choose names carefully as they play a crucial role in the self-documenting code approach. When self-documenting code falls short, it's time to investigate. It's essential to figure out why it's no longer effective. Possible causes may include deviation from naming conventions, careless code review, a need for adjustments to current code conventions, an increase in system complexity. The first reason can often be addressed through human interaction and communication. However, the last one is a challenge that we may have limited influence over. If it is the issue, you'll need to start writing comments and supplementary documentation for your code. Commenting on code is an art form, and there are numerous approaches to take. My suggestion is to try the following. Write a one-line comment for the function, no more. If you can't describe what it does in 1-2 sentences, it might still be too complex and needs to be simplified. Only include meaningful comments, don't state the obvious. Keep comments updated alongside the code. The more current they are, the better. While these tips can be helpful, they won't necessarily prevent the need for more substantial documentation. Documenting a small piece of code may be straightforward, but how do we tackle documenting larger features? In this case, comprehensive documentation is inevitable. Follow your company's guidelines, as they may vary. You may be required to write high-level documentation in the form of a README file in the Git repository or in a Notion knowledge base. If you are unsure about the existence of such guidelines, don't hesitate to ask more experienced colleagues or create your own. Thank you for joining me in this bonus lecture, guys. A kind reminder to connect with me on LinkedIn if you haven't done that yet, and check for the MAA book. As you remember, you have a huge discount. Thank you so much for trusting me. See you in LinkedIn. Sincerely yours, Alex Zaitsev.